Today, we're going to continue looking at sequences, series, and power series. Let's remind ourselves of the things that we know about convergence of series. First, we have our necessary condition. If the terms don't go to 0, then the series diverges. That's the first thing that we look at. If the terms do go to 0, then the series might converge and we have more work to do, but at least we know that we have more work to do and that we're not done. The next place we went was the integral test. This was a nice connection between the continuous and the discrete infinities that we've been looking at in calculus. The integral test takes our series and we make a continuous function out of the terms and then look at the improper integral. This was useful because it led us to P series. It gave us we know that the term, it's not important that the terms go to 0, it's important how the terms go to 0. And when we're looking at a P series, that gives us a nice boundary of what's going to 0 fast enough. We saw that 1 over n is not fast enough. That's kind of the boundary. That's where things start to diverge. We're going to 0, but not fast enough. And the integral test is useful because we add 1 to the exponent and divide by the new exponent. So if we have a function of the form 1 over n to the p, if p is greater than 1, when we add 1 to the exponent, the n still shows up in the denominator, and so that term still goes to 0. Where P series became even more useful was when we looked at comparison tests. So here's where we say one series is going to behave like another series. So we just have to make a comparison, and that will tell us whether something converges or diverges. So if something is going to behave like 1 over n, that's going to diverge. If something is going to behave like 1 over n squared, that will converge. So comparison tests are one way for us to say, one way for us to quantify what we mean when we say one series behaves like another series. And then we added to our list of series a geometric series. It is important to add these because we had the P series to deal with rational and radical forms. But the geometric series is going to help us with exponential forms because the n shows up as the exponent. The even better thing about geometric series is that we can actually find the sum of a convergent geometric series. The series as n goes from 0 to infinity of a times r to the n is a over 1 minus r. So we can actually find the sum of the series. So to that end, we had a discussion yesterday, or we were having a discussion yesterday, between these two series that were similar. I had this numerator that was 2 plus sine n. Then in the first example, I went over n, and in the second example, I went over n squared. So the evidence that we collected yesterday was that in both cases, the limit of the terms is equal to 0. That just means that the series don't diverge immediately. We don't just automatically say they diverge. The terms go to 0, so we have to look further to decide if things converge or diverge. Then we decided, we pointed out the oscillation part, that sine n will always be between -1 and 1, so 2 plus sine n will always be between 1 and 3. And then I very suspiciously pointed out that these are all greater than 0. And so now we wanted to, how do we use this information to determine if the series converge or diverge? And that's the answer right there in the chat. The 2 plus sine n over n can be shown to diverge by comparison with 1 over n. So the important part of this statement here is that the 2 plus sine n over n is greater than 1 over n, and the series 1 over n diverges. So for this series over n, we're making a comparison to the series 1 over n. So the important parts is right here. This is what's telling us, this is what's the important comparison here. Since the 2 plus sine n over n is greater than 1 over n, and the series 1 over n diverges, the given series 2 plus sine n over n also diverges by the comparison test. So our argument could look like this. Since the series 1 over n diverges, and since 2 plus sine n over n is always going to be greater than 1 over n, we can say that the series 2 plus sine n over n diverges by comparison. So there's a nice, complete, and solid argument. So when we look at the 2 plus sine n over n, the instinct that we want to build in is that we want to see the 2 plus sine n, that's all just extra noise. What's going on is some constant over n, and 1 over n diverges. What's in control here is the 1 over n part, and so this diverges. Knowing that that first one diverges, what do we think about this second one? So this first one diverges. Here's the important thing. So the first one diverges because the terms here are going to be greater than a divergent series. One thing to note about this inequality is that the fact that the terms of the given series are less than 3 over n is not useful at all, because the series 3 over n also diverges. It doesn't help to try to squeeze something underneath a divergent series, because we're just saying, well, that'll be less than infinity, and that doesn't help at all. So moving over to the 2 plus sine n over n squared, once again, the terms go to 0, and we have a very similar looking comparison. 2 plus sine n over n squared is between 1 over n squared and 3 over n squared. What's going on with 1 over n squared and 3 over n squared that's different than what's going on with 1 over n and 3 over n? So in this category, for this series, we know that 1 over n squared converges, and 3 over n squared also converges. And so we should suspect that this series converges. That should be our suspicion. But we can't use the same argument. It's not useful to say that the series in question is greater than this convergent series, because it doesn't help. If the series 1 over n squared, that's finite. If all these terms are bigger, that could be, maybe it's infinitely bigger. So what's important here is not the greater than part, but the less than part. So for this argument, we're going to want to focus on the second half, second 2/3. The less than inequality. And we'll say that since the series 3 over n squared converges, and since the 2 plus sine n over n squared is less than 3 over n squared, the series in question, 2 plus sine n over n squared, converges by comparison. The reason that I wanted to put these two series back to back is that a lot of times in math class, we can get away with looking at an example and looking at what's similar, looking at when we're faced with a problem, say in the homework section, we just kind of like flip back to that in through that section to find an example that looks like that one and they just kind of imitate. And unfortunately for our heroes, we can't just kind of look at things that look similar, because notice that I set up a very similar set of evidence, but we had to use it completely differently in each of these cases. So we can't just look at the example in the book and say, well, this pretty much looks like that one. We have to be able to read what's going on and know what we're looking at. We're beyond the point where we can just imitate what's going on. Any questions? The other thing that I want to reiterate is that the limit of the terms being 0 in a series does not give you convergence. It gives you maybe convergence, but it could be that the terms go to 0, but the series still diverges. Could be that the terms go to 0, but that the series still diverges, like it does in this case. So it's not that the terms go to 0, it's how the terms go to 0. We need the terms go to 0 plus something else. It's not that the terms go to 0, it's how the terms go to 0. It's not that the terms go to 0, it's how the terms go to 0. What we need is the terms go to 0 plus something else. We need terms go to 0 we need the terms go to 0 plus something else. We need that the terms go to 0 plus something else to get convergence. So in the case of the series 2 plus sine n over n squared, we have that the terms go to 0. That's necessary. We needed something else. In this case, that something else was that the terms of the series in question are less than a known convergent series. That's something else. Or we could think of it as the something else is that the terms are going to 0 faster than the series 3 over n squared, which we know converges. But we need that the terms go to 0 plus something else to get convergence. So there's all kinds of different ways that we need to think about series, the things that we need to look at. The way that we're going to play this game is that I'm going to put 12 series in front of you, for example, and I'm going to give you 60 seconds to decide if the series converge or diverge. And it's just a quick decision making on your part is what we're going for. So I want you to imagine 12 series in front of you, and you just have to pick them off. Absolutely convergent, divergent, conditionally convergent, absolutely convergent. divergent, divergent, and so on. It has to be quick. We have to look at them and decide. I don't literally just give you 1 minute. Even if we were in person, it takes me longer than a minute to hand out the papers and then to collect them. But a fun way to do this, if the class is nice and full, I start on one side of the room. I start and I pass out the papers at the front of the class. When I get to the other side of the room, I just go back to the front side and I start collecting them. Because that's how fast we want to be when we look at the series. We want to look at this in instance to say, 1 over n, that looks like it diverges. 1 over n squared, that one converges. So we're just trying to add to this something else that we can identify, where the terms go to 0, plus we get something else, then we can conclude convergence. Let's look at another something else. How's everybody, okay? All right. Let's look at the next something else. I think it's not just a high pollen day on the coast, it's a high pollen day everywhere. I woke up and it was just like just woke up to just massive amounts of sneezing. So spring is awful. All right. Let's move on to the next something else. So the next big something else is the alternating series test. So the next something else that we're talking about is alternating. If the terms go to 0 and they alternate, then you get convergence. So here's what the alternating series test says. Let's let the sum, as n goes from 0 to infinity, of -1 to the n times an. So if we write this out, what's going to happen is that we're going to have signs that are alternating. So it'll start off with an a0 plus or minus a1, but plus a2 minus a3 plus a4 minus a5, and so on. So what we're going to see is that the signs are going to alternate. So -1 to the 0 is positive. So we start off with a to the 0. But -1 to the 1 is negative. So we have negative a1. -1 squared is positive 1. So we get plus a2. But -1 to the third is back to -1. So we get negative a3. -1 to the fourth is back to positive. -1 to the fifth is back to negative. And this is going to require that an be positive for all n. So let's consider an alternating series. So we're also going to need to let an be greater than 0 for all n. So the alternating refers to the sign. So we've got an alternating series. And here's what the alternating series test says. If the limit of the terms is 0, and the terms decrease, then the alternating series converges. So if the terms decrease and decrease to 0 and alternate, then we get convergence. So this A0, this AN plus 1 less than AN, this is stating that the terms decrease. Limited as n goes to infinity of AN equals 0. This is a necessary condition, so the terms decrease to 0. And the terms alternate. So if those three conditions are met, then the series converges. What that means is that if the terms go to 0 and they alternate, then you get convergence. We have to separate out the terms decreasing and the terms going to 0 because those two things are not always the same. So in our previous example, we had 2 plus sine n over n. Those terms are not necessarily decreasing. The limit of the terms is equal to 0, but the terms aren't always decreasing. So let's our primary example of the alternating series test is the alternating harmonic series. The alternating harmonic series converges. So that would be the series, the sum as n goes from, say, 1 to infinity of -1 to the n, we'll go plus 1 since we want to start off positive over n. So that'll be 1 minus a half plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. So the alternating harmonic series converges. The terms go to 0. So first of all, we take out the alternating part when we look at AN. So even though the terms are alternating, we would identify AN as just 1 over n. We look at the terms without the alternating parts. So when we're doing this analysis where the terms go to 0 and the terms decrease, we have to consider the terms without the alternating part. Otherwise, half the time this is going to be trivial, and the other half the time it's going to be impossible, because the signs are alternating positive and negative. Negatives are always less than positives. Positives are never less than negatives. So we just have to consider the terms without the signs, without the alternating part. We got to let an be positive for all n, so that the -1 to the n is providing the alternating part. So the terms alternate in sign. We could say that since the limit as n goes to infinity of 1 over n is equal to 0, and 1 over n plus 1 is less than 1 over n, therefore, the alternating series -1 to the n plus 1 over n converges by the alternating series test. We have to make sure all of our evidence is introduced. First, the terms go to 0. Second, the terms are decreasing. And then third, the terms are alternating in sign. Then we get to make our conclusion, convergence. First, the terms go to 0. Second, the terms decrease. And third, the terms alternate in sign. So alternating in sign is that something else that could give us convergence. Terms go to 0, and the terms alternate in sign, series converges. It's important to note that sign n does not alternate in sign. Sometimes it'll double positive and double negative. So we're not alternating. It's just changing sign erratically. It's not positive, then negative, then positive, then negative. Here's how we can visualize the alternating series test. The alternating series test has a great visualization. So if we think about consider the sequence of partial sums. For an alternating series. I'll start off positive. If we consider the sequence of partial sums for an alternating series, the first term is just going to be a0. Then the next term will be a0 plus a1, or sorry, a0 minus a1. Then the third term will be a0 minus a1 plus a2. Then the fourth term will be a0 minus a1 plus a2 minus a3. Because the sequence of partial sums just means put on another term. And then a0, it's going to fit. It's not going to fit. Try it anyway. a0 minus a1 plus a2 minus a3 plus a4. So here's the first 5 terms of the sequence of partial sums. If we plot this sequence of partial sums on the number line, if we start off with 0, then the first term is going to be a0. And so that's going to end up out here somewhere. That's going to be a0. I'm going to have to give these names. I'm going to call that S0. Let's say S0 is A0. Now I'm going to plot A0 minus A1. Two things come into play. A1 is less than A0. So when I subtract A1, I'm not going to go past 0. So for S0, the amount that I subtract is going to be less than the amount that I just added because the terms decrease. The amount that we subtract is less than the amount we just added. The amount we subtract is less than the amount we just added. The amount we subtract is less than the amount we just added. Now, if I go to plot S2 or oops, that was S1. When we go to plot S2, we're going to take A0 plus A0 minus A1, and then we're going to add A2. But the amount that we add to A0 minus A1 is less than the amount we just subtracted. So S2 will have to be between S1 and S0. The next term, S3, we just take S2 and we subtract A3 from it. But A3 is less than A2. So the amount that we're subtracting is less than the amount we just added. So S3 must be between S1 and S2. And so we're in this Princess Bride situation. Aha, when we go to plot S4, we're just going to add A4 to S3, but the amount that we're adding is less than what we just subtracted. So S4 will have to be between S2 or S3 and S2, and I clearly cannot choose the goblet in front of me. And so this proceeds forever. Because the amount that we're adding, that we're subtracting is less than we just added, and then the amount that we add is less than we just subtracted, we're always going to be between the previous two terms of the sequence. Therefore, the sequence must converge, because we'll have S5, and then S6, and then S7, and then S8, and so on. So that's how the proof of the alternating harmonic series test works. So this is visually what's going on. If you want to summarize the proof of the alternating series test, all you have to do is, you know those door stops that you bolt into the wall? It's like a little spring with a rubber on the end of it. And then so the door hits that before the doorknob hits the wall and puts a hole in your drywall. You know what I'm talking about? So sometimes it's like a solid piece of metal because they want that thing to punch through the door because they make doors out of cardboard. But sometimes they want to have a little give, so there's a little spring. And then what you have to remember is that if you got sent to your room when you were a kid, and in the days before you had like any kind of video games in your room, and you just had to sit there, you would sit there by the door and just play with that thing. And when you bonked it, those little spring things, they would go back and forth, and they would go brrrr, brrrr. That's the alternating series test. So if someone asks you to prove the alternating series test, the place you should start is just going, ah, yes, brrrr, alternating series test. They'll be like, oh, what? And you go, brrrr. Proof of the alternating harmonic, the alternating series test. Any questions? Really, I do the alternating series test specifically so I can make that noise because it's fun. Brrrr. All right. What we encountered is a series that when it's alternating, converges, but when it's not alternating, diverges. And that's bad. Tomorrow, we're going to see why that's bad. Because tomorrow, we're going to look at the difference between conditional convergence and absolute convergence. All right, that's going to do it for today. Everybody have a good day. I'll see y'all on tomorrow, and thanks for playing.